stop the stream. Alright. So it's time to figure out why the CANOpen driver crashed, and the first thing I'm going to do is just have a look at the device tree, because I think I forgot to specify the required variables in the device tree. So let's see, we have CANOpen, we have vardir, and then we obviously need to have the CAN interface on which this will run. So CAN equals CAN. So I will have one running on CAN1 and another one running on CAN2. Let's see, this will be CANOpen slave. Let's make this CANOpen master. And the other one will be CANOpen slave. Which is pretty nice. Maybe I don't even need any kind of switch between two different modes, and instead just have the master, like if one board is the master, then the other one can just be connected with the second CAN interface as the slave. So this will be in CAN2, and here in CANOpen I have mode is default master. So we can set mode CANOpen slave. CANOpen mode master. And in order to make these definitions work, I have to add a file to the include section here. So let's call it, this is a special set of include files, which I write specifically for the device tree. So we're going to have a file that's called dts CANOpen. And let's see, anything else we need? No, I don't think we need anything else here. So this will go master is 0, slave is 1. Let's see, this is lib driver, so I'm going to add it to lib firmware. And this is a bunch of files that define STM32 stuff for use in device tree. It's good to have a separate file for definitions that are to be used in device tree. So I will check here that all of the options are set. All of the required options are set. So if not CAN, as well. Those are the two things that can cause a crash. So I'm gonna check for them explicitly. It's much easier to debug when there is a message telling what's wrong. And I'll also need to add this file to the make file so that it gets included. Okay, time to power on the board. And the board is, let's see, what the hell is this, the I2C bug again? I2C is on my to-do list. Seriously, what is this? I'm gonna try to flash it. So why is the console not working? This console has crashed. So I killed Picocom, but there's, yeah, this terminal is screwed up. So let's do it like this. What? Not working? Let's see. What if I restart this? Seriously, what is going on? So the LED is blinking, but the terminal doesn't seem to be working. Let's see. Like, what the hell? This is supposed to return to bash when it gets killed. Okay. Now unplug the USB device and see if that fixes the problem. Oh, now it came back. Really? Is the TTY USB completely not working? There's something wrong with this USB hub. It sometimes just totally fails. Let's see. What the hell? Temperature above threshold, really? So now it should be, yeah, now it's back. Let's see if this is back yeah, now it seems to be working. There's something wrong with the hub. I will just go like this and quit PicoCom and go back to my Vim here. Yeah. Okay. Cool. So at least CANOpen is ready. We have CANOpen TX, which is the task that is responsible for sending out periodic synchronization messages. And I don't think I have synchronization set up yet, so I'm going to do that. And I should be getting then the synchronization message every millisecond. So I'm going to configure that, and that will be a good start, just to get a synchronization pulse on the bus. So the way CANOpen works is that you can have the master generate a synchronization message at a given period, and whenever all the slaves receive the synchronization message, they send their process data objects to the master. So everything becomes synchronized in 1 millisecond frames, or whatever time interval you choose to use for sending out the sync pulse. And the slaves never actually, the slaves can be configured to either send out periodically, just without receiving any sync pulse, or send it out when the sync pulse is received. And I like to use the setup where I send out any results upon receiving the sync pulse, because then I can have the master automatically control the load of the bus by adjusting the sync interval. So, CANOpen. I'm going to add a variable here to set the sync interval. It's going to be like an integer specified in the device tree, and default will be 1. And this will only be set up if we are running in master mode. I wonder if there is any. There's a function somewhere that I have that sets the sync interval. So I just want to copy the. I just want to either call the function or copy the code somewhere else. Because it shouldn't be a public function. Empty send, empty reset. No. So now when the CANOpen driver is going to be completely self-contained and only exporting the public interface, there wouldn't be any methods that like things like this that are accessible publicly. So this is how we set the sync period. So what I will do, I could just call the sync period, set sync period here. Sorry for the slight delay. My dog was trying to eat a tennis ball, so I had to take the tennis ball and throw it out. You're not supposed to eat tennis balls, just play with them. So now I can continue. sync interval. I'm gonna make this static as well. And I no longer need the lock here though, so this can be removed. And if sync interval is not 0. So the default will actually be 0. Disabled sync interval. So now, actually I'm going to set it to 10 milliseconds. Or should I? No, I'll go with 1 millisecond. Because I'm running now on 1 megabit, so it's fine to have 1 millisecond. There's plenty of time. Let's see. Okay, so now I'm gonna check if there is any data here. There's no data on the canvas. This is quite ugly, to have a semaphore for stopping like that. Service runner, let's see. So service runner. So one of the things that I think is happening here is that, let's see. No, actually I take that back. The problem is that I didn't configure the sync. Let's see. I need to make sure that the sync object is enabled. What else do we have here? Service runner. So if master and sync not disabled, profile cycle period 0, which it shouldn't be, and T is after sync timeout. master is 0. This should be sending out the messages. For some reason it doesn't. Oh. Yeah, so obviously I have to set the sync interval because I changed it to 0. So sync interval would be 1 here. So I disabled it by default, so I have to set the value to make it work. Oh, and also it should be on the master, not on the slave. Sounds good, Damien. I hope you succeed in programming the ESP chip. And checking the sync. No, nothing coming out. So let's see. Sync interval is 1. I'm going to put this to, let's see, I'm going to put this into auto mode. So I have a continuous signal, and there is nothing being transmitted. Let's see. Scale. Let's make this like 1 millisecond. Yeah. Really? let's see if service runner is running. For some reason, no completion. Very strange. Continue. Service runner. And let's see. Cycle period is 0. What happened? Why did I screw up? Okay. This one expects microseconds, not milliseconds. So let's set this to 1000. Yeah, it's actually better to express it in microseconds. Yes, Mogans, this is my framework. Yes, of course you're interested in the device tree part, because it's the best way to solve the problem. It's you can download this a little bit older code from GitHub, but you will have the implementation of the device tree. It's actually very simple. It's just so basically what I have here is driver. Let's see, actually first I'm going to test this. Yes, so now I have the sync pulses. Let's have a look here. At least I have something that looks like sync pulse. Actually, it looks a bit strange. Scale. Just a level. Yeah, this looks like a sync pulse. It's pretty random right now. It should be. It's more like 5 milliseconds, not 1 millisecond. So this tells me that maybe there is something wrong with the configuration of RTR. Something wrong with the configuration of the SysTick timer that's used for the RTOS. So maybe the sleep period is actually not, like when I do thread sleep 1 millisecond, maybe it's not actually sleeping 1 millisecond. So I have to check that. But I'm going to show you how to do the device tree. So for the device tree, I use libfdt, and I have a driver loader that basically just a few functions, and all they do is there is a function called probe device drivers, and this is the function that I call from main, which takes the device tree as argument, and then checks the header and loads all the subnodes. And then it goes through every single entry in the device tree recursively, and it checks the compatible string to see if it needs to load the device driver, or actually here it goes through the device driver list. So it goes through each node here, and for each node, this is very inefficient, but it's only done once during initialization, so it doesn't really matter. As you can see, the loading is pretty fast anyway. So it loops through the list of device drivers which are registered in the system, and it calls the probe method for each device driver, which is compatible with the device tree node. And init modules is right. Actually, it's this method. Sorry, this is deinitialization, but it's the same concept. And the probe method is defined for each device driver as part of the source code for the device driver. So I have like probe and remove here. And the probe method takes a pointer to the device tree and the ID of the device tree node. And to load the device tree, I use libfdt. There is a modified version that is available on my GitHub, where I've added functions like, for example, get int or default, which is very useful. And I think I added a few other things. I don't remember exactly how many changes I made to it. So the device loader calls the probe method, and the device drivers then register themselves with corresponding subsystems using, for example, this is a UART driver, so it will register a serial interface. So it's going to register a serial device. When it has registered that, then other drivers can query the serial subsystem for serial devices. And what they usually do is then they pass the device tree reference. So in the device tree, you can have a reference to a node, which the device tree compiler will complain about if the reference does not exist. So you can always be sure that the reference exists in the device tree. And then you can retrieve the reference from the device tree and use that reference. You retrieve the device node ID for that referenced node, and from that I can then search for a corresponding serial interface that corresponds to that device tree node. So in serial device init, I pass the device tree and the device tree node to this serial base device, the base class for serial devices. And in the driver H, I have a few macros that help declare the device drivers and device tree classes, and this is just very crude templating of the subsystems. And the interesting part is the device driver macro, which I use in every device driver. And what I do here is I define a function that's called the device driver name, and with the suffix ko, kind of like a kernel object. But yeah, the only purpose of that suffix is to make sure that this function is somehow different from any possible other symbol that may be defined somewhere else. So for example, if I have like vardir is the name of the driver, so vardir underscore ko is going to be the name of the function that initializes that driver. This is defined as a constructor, and everything would have been very simple if constructors were run when they're compiled into archive library. So if I have a static library and I have attribute constructor on some functions, they're not actually going to run when I link the library. To solve this issue, I then specifically include the functions that initialize the drivers that I want to use. So it's actually a benefit to have it that way as well, because when you have a constructor that initializes the device driver like this, it's actually including the probe and the remove methods into the compilation unit. So you can't really, like, if you compile a bunch of drivers and you only use some of them, since the probe method is included, most of the driver is basically included then, because everything is referenced by the probe method. So the fact that static libraries, constructors in static libraries are not included by default is actually a benefit. So I specify the functions or the drivers that I want to include then in the make file when I link the executable, and I do it like this. Currently it's just a command line to the linker where I specify WL, so linker option, and then I define this symbol explicitly. So when I define it explicitly, then the linker will try to link that symbol from the library, and then everything works and everything gets included. And that's it. That's basically how I work with the device tree. I don't know what else is worth looking at with regards to device tree. All right. Hope that answers your questions about my use of device tree. I think this is a very good way of doing this. I would love to see more projects use device tree. I think device tree is really the way to configure a firmware for different targets. Okay, so I have a sync pulse, so that means that I can continue my work on the CANOpen interface and implement, or actually, I should actually move the CANOpen profile definition from the CANOpen driver and move it outside so that I can define, for example, the motor driver profile, the 402 profile separately instead of always defining it in the CANOpen driver. So that's the code that I've commented out from my CANOpen driver. And I have many repositories on my GitHub which are old versions of this code. So I started with, it was called libk a few years back, and that was a project that I started where I wanted to kind of gather many different little drivers that enable communication with I2C devices and SPI devices. And then I I explored this idea of using proto-threads slash non-threaded approach where you have just one thread and you kind of like have this weird code structure where everything runs as part of the same loop, but it appears as though it's kind of threaded, which was a complete failure. Like, after doing that for I've been exploring that in detail for maybe about a year, and after doing that, I'm pretty convinced that anything that looks like QP or like proto-threads is just bullcrap. It's the best way to destroy a project. Then I basically continued working on that, and that turned into libdriver, libstm32. So there's a lot of projects that I have, like older repositories that contain old code, which I don't use anymore. And now it's called the boss. Yeah, I have a very vivid imagination about naming my projects. I couldn't come up with a better name. Like, I don't know. It's better than libfirmware, at least. It's kind of the software that controls the whole board, so I call it the boss. Yeah. Okay. So moving on then to implementing the CANOpen profile. So the way CANOpen works is that you can have different profiles which are like documented online from different manufacturers, and you can also buy the official documentation from CANOpen Alliance or whatever they're called. So they're not actually open. CANOpen is not open. That's the big truth about CANOpen. You define a profile by basically defining registers that the device is providing to other devices on the network, and through those registers you can kind of have like a standard way of controlling a certain type of or certain class of devices on the bus, such as, for example, a motor drive. And using the old Vardir code, the basic set of fields that I would define for a 402 profile are these. So you have like a register for device type, sync ID, cycle period, and all of these things can then be changed by another device on the bus. So as long as basically this CANOpen driver provides means to access internal variables, internal registers of the board, so it becomes very powerful. It allows very flexible configuration of the network, just as long as you export the necessary variables through this variable directory. So this is something that I need to now move to the CANOpen profile definition, and I wonder how I'm going to implement that. So I have the device tree. What would be a good way to implement the profile? And the profile is actually also, it's kind of at the highest level. It's almost at the level of application, because the profile, anything that gets written to these registers are values such as, for example, user inputs maybe. So if you have like joystick connected to CAN and you want to read the joystick, you have the CAN master program that joystick to send out data, and the data automatically gets mapped to registers on the CAN master or some other device. So it could be any device. So you can say like, okay, I want to have the joystick send the joystick value with this given COB ID to this other device and map it on that other device to a variable that's internal to that other device. And then once the master starts sending the sync pulses, the network synchronizes itself, so all devices function automatically. And any value, for example, for a joystick would have to be handled by the application. So it kind of ends up being something that should probably be registered by the application. But I have to think about this, so I come up with a good solution, because I don't want to refactor the parts of this CANOpen stuff after I'm done with this wave of refactoring. So would it be reasonable to... So I'm going to start from the device tree, and I'm going to think about what I want to achieve. So what I want to achieve now is having... Let me just bring up the camera here. So what I want to achieve is having this control panel send the data from... Or actually, no, this is how I'm going to do it. I'm going to have the control panel read the inputs and produce motor outputs, and then there will be another board that will act as a motor drive and will just accept the desired motor commands. So this board will run the 402 profile, and this board will be the CANOpen master. So this board needs to have local variable directory entries for reading things like the position of the joystick. So there is a joystick on the other side here. Oh, damn it. The camera is off, so that's why it's going like back and forth. So the camera, because I unplugged the USB hub, I also unplugged the camera. So I'm going to restart the camera. So now the camera is working. So there's a joystick on the other side here. There's buttons and joystick. And this control panel will control the motors. So anyway, so locally I need to have variables in the directory for the joystick, and here I need to implement the device profile for the motor drive. CANOpen slave. Would be the... Okay, how about this? So DS 402. Maybe we would have like compatible firmware. And this just needs to know about the variable directory because it will just register the variables with the directory. But the problem is that there is such a wide array of parameters that essentially belong to different subsystems. So this has to be something that either that I have the different subsystems register their own variables, which is probably the right thing to do, or I have the top layer, like top level application code that will then register the variables and make lower level calls to retrieve the data, which I think is suboptimal. I think it's better to have the individual device drivers push their settings into Vardir, and then I add support for the variable directory to the individual device drivers where it matters. And then the way that this but I have to also think about whether I want to have, for example, this part. So this is an entry for the serial number of the board, right? So I use usually the serial number of the STM32 to get a unique serial number for the board. But also I could use maybe some other chips which have their own serial numbers, so kind of get like a unique identification which is guaranteed to be unique per board. But putting this in the CPU driver, it kind of doesn't make any sense. Unless I would have the CPU driver export variables that are relevant for the for getting information about the CPU, which could actually be an interesting approach for the rest of the system. So if this registry map could kind of act like a generic way of exchanging data between different parts and do it very quickly, then that could be an interesting approach to do this instead of having to add abstract interface methods in order to get the information about some device. So this could be an interesting approach. and then the registry map interface will be standardized within this system. So it would be like, for example, if CPU exports certain registers that represent the serial number, then all the CPU drivers would export the registers at the same offset, and somehow maybe retrieve the CPU serial number, depending on the architecture. And then the higher level software can then read those variables and export the higher level view of the serial number for other devices on the CANOpen network. YouTube is complaining that it's not receiving enough data. Okay, this is probably a very boring topic for a video, so I'm gonna stop this video now and have a little think about how I'm gonna implement the variable directory. And once I arrive at a solution that I'm gonna go forward with, I can record a different video where I will actually implement that solution. Alright, thanks for watching.